today I'm going to talk about RSA key exchange mechanism. So first of all, if you are talking about RSA, it means that you have two parties, Alice and Bob. Alice will have two keys, secret key and public key. It will send its public key to Bob, and Bob will take some message M, and using a public key, it will encrypt it to message M prime, which can be safely transferred to Alice, and Alice can decrypt that message using secret key. So from M prime, it can get M. Okay, in order to explain how all this works, I will need some math explained first. So first of all, I would like to talk about a ring. A ring is an algebraic structure, and it's denoted as Zn, where n is the size of the ring. It's a set of elements from 0 to n minus 1, such that there are two operations defined on the ring: operation plus and operation multiply. I won't talk about all the caveats of rings, but I will just tell that the simplest way to define these operations is that plus by modulo n and multiply by modulo n. If we have, for example, a ring of Z8, then it will be a set of all elements from 0 to 7. And let's say 2 plus 7 in this ring is going to be equal to 1, because it's 2 plus 7 is 9 and mod 8 is 1. And if you take 2 multiplied by 7, it will be equal to 6, because 2 multiplied by 7 is 14 and mod 8 is 6. Okay, what's other important thing about this is a notion of a revertible element. An element is called revertible if there exists some other element in the ring such that multiplying these two elements will result in 1. So for example, 7 is revertible in the ring Zn, because multiplied by 7 it will be equal to 49, and mod 8 is 1. The same holds for 3. 3 multiplied by 3 is equal to 9, and mod 8 is equal to 1. However, 2 is not revertible. So 2 multiplied by 8 is never equal to 1 for any a from Zn. And you can check that if you want. Actually, not from Zn, from Z8. And there is a lemma that says that a is a revertible only if it's co-prime with the base of the ring. In other words, greatest common divisor between m and a is equal to 1. So for the ring Z8, the following elements are revertible: 1, 3, 5, and 7. And the set of revertible elements for the ring Zn is denoted as Z star n. And in this case, we have Z star 8. Okay. Now let's talk about Euler function. So Euler function is denoted as phi from n, and it's equal to modulo Z star n. Or in other words, it's equal to modulo Z star n. Or in other words, it's equal to number of revertible elements in the ring Zn. Let's make some interesting observations. So if n is prime, then phi from n is equal to n minus 1. Why is that? Because if n is prime, then it's co-prime with every element in the int except for a 0. That's why we substitute 1. If n is equal to product p and q, where p and q are both primes, then phi from n is equal to p minus 1 multiplied by q minus 1. Why is that the case? Let's open the brackets. So it's equal to p multiplied by q minus p minus q n plus 1. If you remember, p and q is equal to n. We subtract all the numbers that are divisible by p, we subtract all the numbers that are divisible by q, and we add 1 because we subtracted 0 element twice. Okay, now let's talk about Fermat-Euler theorem. Fermat-Euler theorem says that for any x from z star n, the following is true. X power phi from n is equal to 1 in the int zn. In other words, if you take any irrevertible element and put it in the power of number of irrevertible elements in the int zn, then you'll get 1. Okay, now we have everything to explain what secret key and public key are. So what A does is that it picks two numbers, P and Q. Those numbers should be prime and they should be way big. Order of 2 power 1024b. In other words, we use 1024 bits to represent these numbers, or 128 bytes. Then we make n equal to product of p and q. Why is that? Why do we need that? So we need that because knowing p and q, you make it really easy to compute phi from n. And knowing just n, you make it really hard to get what p is and q is, and what the phi from n is. Okay. Now we'll need to pick two numbers, a and b, such that their product is equal to k multiplied by phi from n plus 1. Or in other words, their product minus 1 is divisible by phi from n. Once that's done, we can define public key as n and a, and the secret key as n and b. Okay. Now we can distribute our public key to Bob, and Bob can take his message n and encrypt it by putting it into power a in the int zn. So n power a. And Bob can safely transfer that message to Alice. And what Alice can do is that she can take this message m power a and put it in the power b. As we remember, a multiplied by b is equal to k phi from n plus 1. So m k phi from n plus 1. And that's equal to m power phi from n power k multiplied by m. As we remember from Fermat-Euler theorem, m power phi from n is equal to 1. And 1 power k is also 1. And 1 multiplied by m is m. So after putting m power a into power b, you get m back. Cool. However, for all this work, we need m to be from z star m. And that's really inconvenient because a lot of the messages won't comply with that rule. So what is really happening is that we are not using this for encryption. What B does, it picks some x from z star n. And it uses SHA-1 from x as a symmetric encryption key. And then it can safely transfer x to Alice. She can also compute SHA-1 from that x and also use it as a symmetric key. So Alice and Bob are really using symmetric encryption. They are just using RSA for key exchange. So that's everything I want to explain today.